Hello everyone, and welcome to session number 4 of this set of videos created to explore programming applications in reinforced concrete. In session number 4, we will be using Maple from MapleSoft again, but this time to explore a Maple document that is created to perform flexural analysis of flanged reinforced concrete beams subjected to negative bending moments. Negative bending moments occur usually at the support sections, where the flange is under tension and the bottom of the web is under compression. This means that the tension rebars will be placed in the flange and the compression zone will always be rectangular in shape and located in the web. A flanged beam can have a T or L shape, where the flange is usually part of the slab system and the web is the drop of the beam below the slab. If the bottom steel running from midspan into the support is taken into consideration, then the flanged beam is treated as a doubly reinforced beam. But if the steel running from midspan is used only to hold the stirrups in place, then the beam can be treated as singly reinforced. Therefore, we have 4 cases here. We have T-beam, which can be either singly or doubly reinforced, and we have L-beam, which can be either singly or doubly reinforced. The ACI code requires the tension steel in the flange to be distributed within a region equal to the smaller of B effective, which is the width of the flange, or the clear span of the beam divided over 10. I will show you in a couple of minutes why I am showing a second layer of tension steel in the figure, although usually not required. But first, let us look at the Maple document that I created to perform flexural analysis of flanged reinforced concrete beams carrying negative bending moment. This region here is the region where the user is required to insert the input parameters. Let's go through them one by one, and bear with me please because they are a bunch. We have the depth of beam, thickness of flange, width of web, yield stress of steel and compressive strength of concrete. Then we have the number and diameter of bars in the tension layer that is farthest from the neutral axis, which is usually the layer that is actually required. Then we have the number and diameter of bars in the second layer of tension steel, which is only required in the case that you are performing a retrofitting and rehabilitation case study where you are analyzing an older beam where the tension steel is jammed in the flange within the region encompassed by the stirrup. Then we have N cycle, which is the number of cycles required in the iterative procedure to calculate the stress in the compressive steel when the beam is treated as doubly reinforced. Concrete cover, diameter of stirrups. Now, if the steel is distributed in one tension layer, then we need to specify the number of bars that is spread within the region inside the stirrup and the number of bars spread outside the region encompassed by the stirrup and distributed evenly on both sides. Next, we have 2 identifiers. The first identifier decides whether the section is to be treated as a T section or an L section, while the second decides whether the section is to be treated as singly reinforced or doubly reinforced cross-section. Next, we have the parameters that are required to calculate B effective. The user can insert a given value for B effective, and thus it will not be calculated in the Maple document, it will be taken as given. And if it is not given by the user, if here we have if B effective given is 0, then the Maple document will calculate the required value of B effective. S is the center to center distance between beams. LS is the length of beam center to center between columns. Column B is the dimension of the columns in the direction of beam length. And L clear is the clear length of the beam between columns. Let's run the first case using the input parameters that are shown on screen. Here we are dealing with a T-shaped cross-section that will be considered as singly reinforced. The beam has a single layer of tension steel consisting of 8 bars 20 millimeters in diameter. These 8 bars are distributed as follows. 4 of them are within the region bounded by the stirrup, and the other 4 are distributed evenly on both sides of the stirrup, as you can see in the figure of the cross-section here. When we run the Maple document, Maple will print the required results. Maple will perform all the required calculations to check whether the section is adequate or not. It satisfies the ACI code requirements and then prints the designer's strength, shows a figure of the ductility of the beam, where we can see here that we are in the tension controlled zone and thus the beam is acceptable. And here you can see a figure of the cross section that demonstrates the position of the steel rebars, the stirrup, and the depth of the compression zone, which is at the bottom of the web. If we change the input parameters so that this beam will be treated as a doubly reinforced concrete beam, where the compression steel will consist of 3 bars that are 20 millimeter in diameter, and run the Maple document, you can see here that the beam now takes into consideration the presence of compression steel in the figure and in the calculations. Maple has decided that the compression steel did not yield, and thus we will need to use the iterative procedure to calculate the stress in the compressive steel. Maple checks all the requirements of the ACI code and, if satisfied, prints the designer strength, shows the status of the beam as tension controlled, and then shows the figure that demonstrates the tension steel and the compression steel as well as the depth of the compression zone. Let's say we have a case where we are trying to perform rehabilitation and retrofitting study on an older beam that has been designed using the older versions of the ACI code, where the steel is stuffed within the flange but within the area encompassed by the stirrup. So let's say we have 8 bars that are distributed in 2 layers, 4 by 4, and let's treat the beam as singly reinforced, and this time let's specify a value for B effective. This value is given so that the Maple document does not have to calculate it. If we run the Maple document, then here you can see that the steel comes in 2 layers. Now the new ACI code requires the steel to be distributed in a distance within the flange equal to the lesser of B effective, or the clear length of the span divided over 10. So this here represents an older case or an older beam that has been designed using older design procedures, where the steel was stuffed within the area encompassed by the stirrup within the flange width. If we change the type of analysis from singly to doubly, then the steel in compression will be taken into consideration, and the Maple document will treat this beam as doubly reinforced. Next, we will change the input parameters in order to study an L-shaped cross-section. So here, let's change this to 2, and first try a singly reinforced 4 by 4, leave all the other parameters as is. Then the beam here shows an L section that is treated as singly reinforced cross-section, and if we change the input parameters here to 2 so that Maple will treat this cross-section as doubly reinforced and insert the value for B given as 0 that Maple calculated, then we will get another L-shaped cross-section, but this time this L-shaped cross-section is treated as doubly reinforced concrete beam. This concludes the session for today. Thank you very much for being with me again, and hopefully I will see you in the upcoming sessions. Best wishes.